Yeah, okay, started. So before going to the discussion, we would just like to introduce ourselves. So hi, this is Ishita, and I have Manish with me. Manish, can you switch on your video?
Yeah,
Yeah. So hi, we are from first year, and now I don't think there is any need of any further discussion. So we will directly come to today's session. We have Swagat. He is going to discuss about inflation today, I guess. And of course, there is no introduction needed for him. I guess all of you know him much better than we do. So, Swagat, over to you.
Thank you, friends. Okay, let me make it full screen.
so that before you begin, I was
Yeah.
thinking
So,
maybe I can ask Ishita, how do people plan to integrate the questions? As in, we wait till the end, or we put it in the chat sometime and Swagat checks in between, or how do we do that?
That is up to the speaker. Swagat, whichever would you prefer?
yes, yeah. So that should be up to the speaker. For this particular talk, what I'm going to do is in every about 15 minutes or so, I have 3 different sections in my talk. So I'm going to stop in between and take questions. And in the meantime, please, if you want to type your question, you can type, or otherwise, when I stop and request you to ask me questions, then you can ask. Okay. Sure, great.
Also, we have planned to upload this thing in YouTube. So, this whole session will be get recorded and you can get in touch with it later.
So we have to be careful about what questions we ask now.
No, it's all right. Yes, all right. So let me start. Otherwise, we'll be late. Great. So I'm going to go back. Sorry. In. Great. Sorry, there was some trouble with my Zoom. Okay, great. So I'm going to talk to you about inflationary cosmology. Before I start talking, let me state that uh, this is a theory which has not been completely tested. So let's consider it as a leading hypothesis about the origin of universe, certainly about the origin of structure in the universe. Okay, and this is a fairly important topic in science, just like planetary science, organic evolution, mm, stellar physics. This is also a very important topic in science, and for a lot of deep thinkers, they usually value it as one of the greatest ideas in the last 100 years after quantum mechanics. So since this is so I thought that would be a topic to talk about in the first talk. But it also happens to be a fairly technical and very difficult topic to understand. Okay, so I have made this talk how do I say, oversimplified. Okay, so everything that I'm going to say will be extremely oversimplified. Okay, and later, one, if you hear the talk and you get interested in this topic and you want to learn the details, then we can just talk anytime, or I can just provide you good references. Okay, so let's begin on cosmic inflation. But before I talk cosmic inflation, let me just say for about 10 minutes about uh, the standard cosmology. Okay, in case some of you have never done a course on cosmology, or if you have forgotten about cosmology completely, this would be very easy things for most of you. But nevertheless, I'm going to talk about it for 10 minutes because there are a lot of confusion regarding what is the Big Bang theory. And even even senior people, including professors, have this confusion, and they always have a wrong understanding of what Big Bang theory is. So let me just state that first. So if you look at our universe today on larger scales, if you take a chunk of sky in some direction and then point a telescope towards it, what we are going to see within a 1 square degree angle is about 10,000 or more galaxies in the universe. So universe is today is like a island of galaxy. There are many galaxies. But rather than looking at 1 square degree, suppose I was a Superman and I was a superhuman and I had a bird eye view, then the universe will sort of look like this. Now, this photograph is not an actual photograph. This is a computer simulation of dark matter. Where are the dark matter in the universe? But it's fairly a good, if we can look at the universe, then it will fairly look like this. Okay. Now, what we see is like a three-dimensional spider wave network, where each dot, you can think of it as a galaxy. Actually, in this simulation, it's just a dark matter particle, but you can think of each dot as a galaxy. So there are some places where you see very clustering of galaxies, and there are some places where there are voids. Okay, so that kind of clumpy web structure is what our universe looks like if you look at the universe on a very, very large scales. Okay. However, this is not how our universe looked in the past, and this is also not how our universe will look in the future. Okay. So let's first go to the past, because the past of the universe was very, very different from this picture. The fact that the past was very different from how it looks today is called Big Bang theory. Okay. So Big Bang theory doesn't necessarily have to have any bang in it. Okay. It's a very, very bad nomenclature. It's a theory where universe was supposed to be very different in the past, and it was evolving, and it looks very different today. That is what is Big Bang theory. I'll state it more carefully a little ahead. Okay. Now let me start with complete basics. Uh, People who know it, I'm sorry for you. This will be boring for you. Now we have usual Newton's theory of gravitation, where we have mass, and mass create gravity. And if you have two masses, the gravitational force between them is always attractive. Okay. But that is not true for Einstein's theory. In Einstein's theory, gravity, which is treated as a force in Newton's theory, becomes curvature of space-time. Or even if you think more physically, it says how the distance between 2 points in space changes with time. Okay. That is what is gravity in Einstein's theory. And it is not caused by just mass. It is caused by mass or any sort of energy. Pressure, viscosity, momentum, all of these contribute. In the sense that if you have a spherical object of mass m, you have another spherical object of the same mass m. In Newton's theory, both of them would have same gravity outside their mass, right? But that's not true in Einstein's theory. If the material is different, let's say one is a gas which has some pressure, it will have different gravity. Its gravitational force or the way it pulls objects will be slightly different from a pure object which has no pressure and just a solid. So that's the difference between Newton's theory and Einstein's theory. And also another important thing is in Einstein's theory, the gravitational force could be both attractive as well as repulsive. So gravity doesn't always attract. And the theme of today's talk is to talk about a repulsive gravity. So I'll come back to it in a while. Also, massless particles can gravitate in Einstein's theory. Okay. One of the examples of Einstein's theory is that a black hole spacetime. Okay. A black hole is a structure of spacetime, so geometry of spacetime. That's the example of one sort of gravity. The other example is what we are going to talk about, which is cosmology. So if you take matter, whatever matter you have, and you spread it sort of homogeneously all over the universe, if you spread it in that way, then the metric of the universe, according to the metric of the universe, would look in this particular way, this form. It has nothing to do with Einstein's theory. It has to do with the fact that it is homogeneous and isotropic distribution. What Einstein's theory says is that there will be a scale factor sitting in front of the space distance between 2 points, and that scale factor has to be time dependent. So as time goes on, distance between 2 points is just going to change. Either it's going to decrease or it's going to increase. So that's the consequence of Einstein's theory. It was a prediction. When Einstein solved his equation, this came up as a prediction. Okay. Now, if you have a space-time which looks homogeneous and isotropic, but distance between 2 points in space increases or decreases, then how that quantity, that scale factor A increases, is usually given from Einstein's equations as what we call the Force-Friedman equation. This is simply an equation which says at what rate the scale factor will change, either expand or contract, depends on what is the energy density of the universe. Okay, so I have smoothly distributed matter everywhere, so it is same density everywhere. Depending on what the density is, the rate of expansion of the universe or contraction of the universe will be decided. And whether that rate will change, whether it will accelerate as it expands or accelerate as it contracts, will depend on a combination of density as well as pressure. So see, this term will never appear in Newton's theory. This pressure has no role. But in Einstein's theory, you need a pressure. Okay, and pressure contributes. So whether the expansion or contraction of space will be accelerated or decelerated depends on a particular combination of rho and pressure. Okay. Now in our universe, as far as we have figured out in our standard theory of the universe, that the kind of energy densities we have consist of all the normal atoms that we have. They're in a vaguely and in a wrong way called baryons. But okay, let's stick to that name. So baryons, and then photons, and then neutrinos, dark matter, and dark energy. In a different talk, where I would have focused my talk on the late universe, I would have talked a lot about dark matter and dark energy, but today I will not talk about dark matter and dark energy, and also not about this normal matter, which belongs to standard model of particle physics. Okay, all this matter we know of very well. Now, as I stated a little before, that Einstein's theory says that this scale factor cannot be zero. It's very there is a particular fine-tuned way to make it the scale factor to be a constant, so it doesn't change with time. So universe doesn't expand or contract. But that's a very unstable system, and if one star goes through supernova, the whole universe may either start expanding or contracting. Okay. So for all practical purposes, uh, space has to be either in distance between 2 points in space either has to increase or decrease. That is a prediction of Einstein's theory, and it was observed by Edwin Hubble that actually it is increasing. So one of the solutions is realized in our universe, that our universe is expanding. That is the expanding universe theory. Now, if we look at the history of our universe, how universe expands, by now in 21st century, we have actually measured how the scale factor has been expanding as a function of time for the last 13.8 billion years, very, very precisely. Okay. And what we have seen that since last 5 billion years, universe has been accelerating. So the space has started to accelerate a bit. That is because of dark energy. But for most of its history, in the past, universe has been decelerating. Okay, so universe has been expanding but slowing down, slowing down, slowing down. Now if we take this if we take Hubble's observation that universe is expanding today and go backwards in time, so extrapolate towards the past, what we will see that there will be a time where the density and the temperature of the universe will be very high, because everything that is very far away today would be very close to each other. So universe will be hot and dense. And if the temperature was high enough, so if you keep extrapolating back and back in time, then universe will be so hot that the entire universe will be in the plasma state. So there will be no free atoms. So all electrons will strip apart from nucleus, and all we will have plasma state. So if you have a plasma state in a universe, and if light is propagating in a plasma state, it will get kicked around by electrons and protons. So light cannot travel very freely far away because it's dense, so it meets a lot of electrons on its way and doesn't propagate easily. So universe was fuzzy and light was trapped in the entire universe. But it was expanding, so it cooled down and density dropped down, and eventually neutral atoms started to form. So electrons and nuclei combined to form neutral atoms, and then this light could pass through. And this is a very simple thing because light can pass through neutral atoms. You can see me through my camera because even though there is air in this room, because light just passes through, most of the light. So for the first time, light started propagating in the universe at that time when the first atoms were formed. That's the time when the age of the universe was roughly about 4 lakh years, 3,80,000 years. Okay. So if this was true, uh, if Hubble's observation, if you take Hubble's observation and extrapolate back in time, then we should see a light coming to us from all directions. Plus, the light should be thermal because before coming out, it got kicked around by a lot of electrons, so it was interacting efficiently, so it was thermal. So, and then that was obviously discovered, as all of you know, and it fitted a thermal blackbody radiation very, very perfectly. So perfectly that to see the error bars, you have to extend the error bars by 400 times so that you can see that there is error bar. So there is deviation. I mean, the data has error bars. So otherwise, it's just fit very, very well. Okay. And not only that, it is a blackbody radiation, it has the same temperature all across the sky. Okay. So that was the beautiful confirmation that our universe was in a plasma state in the early universe. And then today it is not in a plasma state. I mean, not in that way plasma state. Of course, there are stars today, but it evolved. Okay. And this is where there was a competing theory, which is called steady state theory, was completely disproved because this will not happen there. Universe was never in a hot, dense plasma state early times. Okay. But if this was the case, if universe was in a hot dense plasma state, and it had the same temperature everywhere all across the sky and same density. Then after it made a transition from the plasma to the atomic state, all we will have in the universe is a lot of gas, but it has almost same density everywhere, very, very smooth. So, and the gas will just expand with the expansion of the universe, and we'll have nothing today, just dilute gas in the universe. Hydrogen, helium, maybe a little bit of lithium. But that's not true. We have a clumpy structure today of galaxies, stars, everything. Okay. So that means that the early universe cannot be completely smooth, even though it was almost smooth. So even that has been confirmed, that the early universe has fluctuations in the density and temperature. The temperature and density in the early universe were almost the same everywhere. The fluctuations were only in the level of 10 to the power minus 4. So if some point in the universe had temperature 5000 degrees, the other will also have around 5000 degrees. So it may be 5000.00001 degrees. So that level of homogeneity was there, but still this little inhomogeneity was present. So before coming back to origin of structure, let me just state, this is what is your Big Bang theory, by the way. In the very early universe was hot and dense, and it was dominated by radiation, basically light. The density of the energy density of photons and neutrinos were higher than the energy density of dark matter, normal atoms, anything else that you know of. Okay, so it was radiation dominated in the early universe, but radiation density in Einstein's theory falls faster than the matter density. So after a while, it made transition to a matter-dominated epoch. And only now, very close to the present epoch, it started to accelerate because of dark energy. Okay, this is your Big Bang theory. It has no bang anywhere. It just says it was a plasma state and it made a transition to a non-plasma state. Okay, that's great. But how did structure form? Okay, so what I said in the previous slide, just to repeat, it made a transition from a plasma state to a cold gas state. Just a minute, somebody is knocking. Sorry, we were meeting. बाद में आओ. Sorry. Yes, but if there was no fluctuations present, then we will just be universe will be just made up of dilute gas today. So we need tiny fluctuations to form galaxies, stars, planets, and eventually Earth. Now the density fluctuations that we have measured already, or the temperature fluctuations, their square, or what we call the variance, would be around 10 to the power minus 9. This has been measured by observation. And how it was measured, if somebody has forgotten about it, there was Kobe satellite which first measured these fluctuations on large angular scales in the sky. Then WMAP and Planck made it even better, and we have seen fluctuations starting from 1 arc minute in the sky all the way up to 180 degrees. Okay. Now, if you start with these fluctuations, so the universe is almost homogeneous and isotropic at early times, but there is small fluctuations. You start with it and let gravity do the work. As universe expands, slowly wherever there was slightly higher density will start to collapse. And so it will evolve slowly to more clumpy, and finally to the spiderweb kind of structure that we have seen today. So yes, so since the initial fluctuations were extremely small, the growth takes about several billion years to form first galaxies and 100 million years to form first stars. So everything happened very slowly. Okay, and this is the Big Bang theory, even in the perturbation level. So we first understood how the overall space and the homogeneous state of the universe evolved from plasma to a gas state, and later we saw that the small fluctuations grew to form galaxies and stars. Okay, so this was too basic, and this is over. I have shown you this. So universe went from radiation domination to matter domination to finally dark energy domination. That's the story. And because of this story and a lot of observational evidences, this is now 100% sure. Okay, if tomorrow somebody finds something different in this theory, it is not going to change this picture completely. It might add a little bit here and there. Maybe it will change our future, or it will change our past even before this epoch, but it's not going to change this part which I said. From about 1 second of universe age all the way up to 13.8 billion years, we know the universe 100% well what was happening. Only the details could be filled in. Okay, that is the standard model of cosmology. So it has become to a state that it is called standard model, just like standard model of particle physics, and it is usually called flat lambda CDM model. Okay, I'll come back to the flat part in a minute. It's called lambda CDM model because in this model the dark energy is a constant, which is called cosmological constant. It doesn't evolve at all. It's all the time a constant. So that's the symbol lambda, and it has cold dark matter. The dark matter has a particular property that they cluster off to very, very small scales. Okay, so it's called cold dark matter. This is the standard theory of cosmology, and it is very successful, and it is 100% correct. Of course, what can change is maybe this lambda is not exactly a constant, but it changes a little bit. Maybe it changes in the early universe. That can change. Maybe the cold dark matter doesn't cluster at all scales. Maybe below galaxy scale, it doesn't cluster. It has some kind of pressure, so it doesn't let things cluster. These things can change, but the overall large scale picture will be absolutely correct. So this is a very successful scientific theory. Now, I'll stop here if anybody has a question here before going next to more important stuff. This was, of course, very basic, but in case somebody wants to ask a question, please.
Yeah, either you can raise your hand or directly unmute yourself to ask questions.
Hello.
Hello.
Yeah. So in matter and radiation dominated era, does the universe was decelerating?
Oh, very good question. Okay, thanks. Just a minute. Something happens when I do my full screen, and when I go back to full screen, it doesn't go away. So I had to do some weird technique too. Okay, let me open it. Yes, Vishwanath, hi. Yes,
Hello.
so during this radiation and matter dominated epoch, all the time universe was decelerating. Okay, so let me go back to that slide. Okay, here. Yes, so let me share. Great. Can you see my slide now?
Yes.
Great. So if universe is radiation dominated or it is matter dominated, it's going to decelerate. So the standard assumption is that our universe sort of started at some time in the early universe. Maybe when it was about 10 to the power minus 10 seconds old, or maybe at Planck era 10 to the power minus 43 seconds old. It starts like that. And then so it starts being radiation dominated and already expanding and almost in thermal equilibrium. So it starts in that hot plasma state. We usually call it hot Big Bang state. There was no bang. The Big Bang is a misnomer, but we call it that way. It's a hot Big Bang state. It started, and then it has been expanding but decelerating all the way until the present time when it just started to accelerate because of dark energy. That is the standard model of cosmology. Okay.
So if we would have, we would observe the universe during matter and radiation dominated era, then we would not infer dark energy lambda. Is it right?
Yeah. So in the matter radiation era, we saw no dark energy. It's very low. Only today it started to accelerate only today. Okay. So if you measure the rate of acceleration of the universe as a function of time, so as you go back in time and see far and far away objects, you will find that space has been accelerating only since last 5 billion years or so. Before that, it was decelerating. Yeah.
Okay. So we would see. Is it possible that we will find another thing like lambda in future, like
in future, towards future?
Yeah.
If lambda, so we don't know what dark energy is. If it is lambda, it's a constant, then the future is doomed, because universe is going to be this lambda dominated, and a lambda dominated universe expands exponentially. So all other densities will fall down and it will only be dominated by this lambda. So it will keep expanding exponentially, and you will not see another galaxy after a long time, because they will all go away from your view. And probably Andromeda will merge with you, but any far away galaxy you cannot see. So the future will be very different and very sad.
So my question was, if we would see the universe during radiation and matter dominated era, we would not infer the contribution of lambda.
Because it was small, yeah.
So we would not actually find or infer any dark energy. And then probably we are missing something because we are we are not at the age that we could find something. Is it possible? I think.
No, sorry, I didn't understand. Do you mean that here something else existed that we did not know of?
Yeah.
Could be. But so yes, absolutely. There could be something else here which we do not know of, but we are sure that there was nothing whose energy density was high enough at that time. Okay. For example, gravitational waves were there for sure, but their contribution to the total energy density of the universe was so low at that time that we don't state them. I don't plot them, gravitational waves here. Okay.
Okay.
So there could be many other things. Higgs existed for a while. It behaved like matter and then went away and became radiation. And in between, it was in a transition state for a fraction of a second. We don't plot them because their contributions were very low. Of course, these are all the quantities that I'm plotting who has any cosmological significance at least some point of time in the universe. Okay? Like dark energy has a significance now. Matter had significance for about several billion years. And even before that, radiation was dominant. So if you're talking about early universe, you can actually, in some sense, you can forget matter in your calculations. Okay, you can forget matter at very early universe. You can just talk universe as if it's just radiation.
Thanks.
Yeah, Swarnim has a hand raised. So Swarnim, you can go ahead.
Yeah. So I wanted to confirm if I understood this right. So from what you said, so whatever you have explained till now, this is what we will call as Big Bang theory. It has
Yes.
nothing to do with what happens before 1 second.
Yes,
It's
absolutely.
independent of that.
Yes, this is the Big Bang theory. Okay.
Okay.
So it should not be called Big Bang theory. So nowadays we don't call it Big Bang theory. We call it the standard model of cosmology. Okay. Thanks
Thanks.
for asking that. That's a good question.
Okay, so next one is Parsi. So Parsi, you can go ahead.
Um, okay, just to get clarify one point from like your previous slide, you separately mentioned contributions from normal atoms, neutrinos, and dark matter. So here the blue curve, which is matter, is a sum total of all these three, or it includes dark matter as well, right?
This matter is dark matter plus all the atoms and molecules in the universe for most of the history. And only recently, this matter has also contribution from neutrinos. So what I call matter in cosmology is something whose mass mc square is greater than K Boltzmann into T of the universe, in temperature of the universe. Okay. So anything which is non-relativistic is called matter in cosmology, and anything which is relativistic is called radiation. Now, neutrino was relativistic early on, and only today it has become non-relativistic. So today matter also gets some contribution from neutrino. But for most of the history, photons and neutrinos are radiation in the universe, and dark matter and atoms are matter.
And what about that matter, which might be relativistic then by this definition? Does it get classified under radiation, or it still stays under matter?
That matter is non-relativistic for this, okay, at least since this part, since 10 to the power minus 5. Okay. So when the universe was about 1 lakh times smaller than today's size, since then dark matter has been non-relativistic. It is possible that dark matter was relativistic before that. Okay. So then it was a part of radiation.
Okay, so
In
radiation.
fact, sorry.
Okay, so here the definitions of radiation and matter, instead of depending on the particular component, is more properly defined by non-relativistic and relativistic components of the universe.
Absolutely right. So matter and radiation are defined as whether they are non-relativistic or relative. So it's a temperature dependent statement. For all the standard model particles that we know, apart from neutrinos, so the least massive standard model particle is electron. Okay, and electron became non-relativistic around a time when universe was smaller than 10 to the power 10 times today. So when universe was less than 10 billions of the size of today's size, at that time electron became non-relativistic. Before that, it was also relativistic. So if you go to a point when the size of the universe was 10 to the power 15 times smaller than today, at that time, all the standard model particles were radiation, because at that time, standard model particles had zero mass. After that time, there was a phase transition which happened in the standard model, and Higgs gave mass into standard model particles, and then they started having mass. Okay, but that is all before this diagram here.
Okay, thank you.
Any other question?
Saurabh, maybe I can quickly ask.
Yes, sir.
I may have asked this question at some point in the past. So this plot that you showed of acceleration, value, I mean, change of scale factor with time.
Mhm.
I mean, one set of observation from which we know that is through the supernova experiment of the more recent universe. Is there any other probe of getting this? Yeah.
CMB. CMB is our main probe. Supernova is also helping us. Supernova just goes like, so using supernova observation, we can go to a point where our universe was half of today's size. Using CMB, we can go to a point when our universe was about 1,000 times smaller. And then by calculating how much helium is there in the universe, we can go to a time when our universe was 1 billion times smaller. So combining these three observations, we have nailed down the expansion rate. Of course, there is a scope for slightly here and there. If maybe there is something extra, maybe Hubble parameter is not what we think of. But overall, this is correct.
How does CMB observation give us this, help us spotting this?
Oh, yes. That's because CMB, we know at what temperature it will be emitted. Okay, because we know the atomic physics very well. So we know how recombination happens. If we have a plasma, how electrons combine with different atoms. We know that. And from there, we know at what temperature it will be emitted. And then we see the CMB today. So then we know how universe evolved in between by measuring that carefully.
I mean, that we know the initial some temperature. It's that, I mean, and that we measured to be 2.7 something. That's one data point.
No, that's not initial. That is today.
Yeah.
Initially, it will have a temperature around 3,000 degrees.
Yeah, 1,000 times more. The scale factor is 1,000 times more. So that's one data point, but you would not need more data points in between.
Right? No, it has to evolve in between. So what will happen if the evolution history was different? You see these fluctuations here in the sky?
Mm-hmm.
So if the evolution history was different, the clumpiness in the universe will increase at a different rate. Okay, and because of that, these spots will start to distort a bit.
Okay.
So when I said CMB, it's not just the background evolution of CMB, but also the fluctuations. Okay, the CMB fluctuations are very sensitive to how the scale factor was evolving, also whether there was a curvature or not, also how matter was clumping. So that's the main observation from which we know a lot. It's a very good question. I'll explain you what part of power spectrum of CMB tells you scale factor, what part tells you how much dark matter you have, how much dark energy you have. Because to determine the scale factor, you need how much dark matter, how much dark energy, how much radiation you put in this Friedman equation. No? Here, depending on what you put, you get the scale factor. Okay. A very good question, but it's a very detailed answer.
And how does helium measurement help?
Depending on so the scale factor, the Hubble parameter of the universe during Big Bang nucleosynthesis directly determines the helium fraction in the universe. Okay. Now, during Big Bang nucleosynthesis, if you play around with the Hubble parameter, it's very sensitive. So the helium fraction will change a lot. So that's a very good bound of PBN. And you can say, what physics do we know here correctly? We know how nuclear physics. So we know how, let's say, hydrogen and hydrogen combines to give us helium. That we know very well from laboratory. So that we take for granted in the early universe. Then we figure out what rate should universe expand so that you get some fraction of helium. Okay. Hello.
So are there other questions?
Yes, please.
So if there are not, I'm going to ask a small question.
Yes.
So in this slide, what is at the top left corner? What does that dot signifies?
This dot?
Yeah.
Red dot?
Yeah.
This is the point where universe started accelerating. So before that it was decelerating, and then around some time it started accelerating. So that's the point where the acceleration is zero. A double dot is zero. So it will go from negative A double dot to positive A double dot. Okay.
So how sharply defined? I mean, I don't see any error bars in this graph.
No, this is not an observational plot. This is a theory. In theory, you don't directly measure scale factor. What you measure is the components of the universe. You measure how much dark energy, dark matter should be there, and then you measure what is the Hubble parameter today. You use these two conditions to figure out what was the expansion rate all through the history. Okay. And then you cross check at CMB, at Big Bang nucleosynthesis, and then you are fairly sure that nothing funny could have happened. It's not a data point. I just noticed, I just say that compared to the Hubble age, around 0.5, 0.4 value, it made a transition. It's just a theory point.
And also in the temperature fluctuations. Yeah, so are the density fluctuations looks the same as temperature fluctuations?
Absolutely,
Or
yes.
okay.
Absolutely the same. But wherever you have high temperature, you have low density, and wherever you have low temperature, you have high density. So they are anti-correlated. Okay.
Okay.
All right. So let me go ahead. I am in no hurry, and I'll stop until 6 o'clock. Whatever I discuss, I'll stop there. Okay. So there is no worries. So, but next, let's go to very exciting stuff now.
Swagat, can I just clarify one thing?
Yes.
So are you saying that the clumpiness of the CMB is sensitive to the evolution of the scale factor after the CMB was emitted?
No, CMB is not clumpy. The spot size of CMB. The spot sizes of CMB is directly related to the expansion history of the universe.
No, so that was before the CMB. This is essentially related to this clumpiness in the universe when the CMB was emitted, right?
No. All through. After the CMB was emitted until today, if the clumpiness of the universe is different, then the light will get lensed here and there.
Oh, okay.
Okay. So, second thing is, even just forget about the clumpiness of space after that. Even if space expansion will change, keeping the clumpiness constant, then the spot sizes will be different. Think of a spot size which is this big, but universe was expanding a bit faster. So that spot would be a little further away from us, right? So it looks smaller in angle. But we know the spot size in CMB fluctuations very well. So I'll come back to it. I have a diagram about it. I'll explain it thoroughly at the end. Okay. These are very good questions, by the way. But the answer is detailed. Should I go forward?
Yeah, you should go ahead. Yeah.
All right. So I had talked about this. Let me go. Yes. So this Big Bang theory is very well tested, and things can change a little bit here and there, but the overall picture is absolutely correct. It's standard model, but I'm going to call it now hot Big Bang model. Okay, you understand that it's hot Big Bang because in the past it was hot and dense, and there was no big or bang in this model. Okay, but it suffers from a number of fine-tuning problems. That the model works very well if you put dark matter, dark energy, photons, neutrinos into it. You put Einstein's theory of gravity into it. It works fantastically well. It explains everything. But it needs some set of initial conditions which are sort of unnatural in a particular sense. In which sense? In the sense that if space-time in our universe began like this, when it began is completely immaterial. But in the past, if the space-time began being already radiation dominated and expanding and decelerating, if this is how the beginning of the universe is, then we have to set at the beginning a lot of unnatural initial conditions for this universe to evolve correctly. So we have found how the equations, for example, to talk in a physics language, we have found how universe evolves. We have found the equations that explains the universe correctly. We also found what kind of term sits in the equation. Everything is fine. We get the final product exactly as our universe. We evolve the equation, we get it. What is problematic is the initial conditions in these equations. You put in differential equation, you have to put initial conditions to solve. These initial conditions seem to be unlikely. One of the initial conditions is you have to begin the universe at whatever time you began, let's say classical universe or at Planck time. At that time, the entire universe has to be completely homogeneous and isotropic at that time. Okay, so which also means that breaking causality, because if universe began at a particular time, all this matter began at that time. How is it that everywhere in the universe the density was same or temperature was same? If somewhere little higher temperature, why did that high temperature got thermalized very quickly on very large length scales? Because light will take some time to propagate from one point to the other. This is a very difficult concept to explain, and it will take 5 minutes, but I'll come back to it at the end if people have questions. But it has to do with the fact that how much light traveled since the beginning of the universe until CMB was emitted. There is some finite distance that light will travel. That distance in the CMB sky today makes only 1 degree angle with us. So we are at some point, CMB is coming from that epoch when universe was 1,000 times smaller. And until from the beginning until the time when universe was 1,000 times smaller, light traveled some distance. And we see that distance today is making about 1 degree with us. That means in the entire CMB sky of 4 pi solid angle, only 1 square degree should be in thermal equilibrium or same temperature and density. All other patches should have different because there is no communication between them. And yet the entire CMB sky has same average temperature. So that is called horizon problem. Why the entire universe is smooth at so early times? It should take more time to get smooth. The second is called flatness problem. This is again takes some explanation to explain, but I'll explain physically. What it means is that if you have decelerating space in Einstein's theory, and if you draw a triangle, okay, if you draw a triangle, if the angles of the triangle, if you add them up, it is not exactly 180 degree. It is 180.01 to start with. And then you let the universe evolve and decelerate. Then what would happen is that as time goes on, it will go away from 180.1 and it will become higher and higher and become 10 to the power 20 by today. So it will become a highly positively curved universe if it was little positively curved at early times. Similarly, if the angle was slightly lower, if universe was 179.99 degrees to start with, if you make a big triangle in the universe, then it will get more squashed and it will deviate and become lower than 180 more and more. By today, it will be like 10 to the power minus 20 degrees. So if universe was slightly positively curved, it will become more positively curved with time. And if it was slightly negatively curved, it will become more negatively curved with time. So as time passes on, curvature will increase, space curvature. Okay. But today, when we measure the space curvature, we find it to be 0 up to 3 decimal places. So if today it is 0 up to 3 decimal places after increasing for 13.8 billion years, then early times it should be close to, curvature should be close to 0, or addition of angle of the triangle would be equal to 180 up to 30, 40, 50 decimal places. So somebody has to set the universe that way. Anytime a dimensionless quantity which appears in physics, it should be of the order of 1. 10, 100 is fine, 0.1, 0.001 is fine, but not 10 to the power minus 50, minus 60. Okay, so that is a very unnatural condition. But if you set that condition, you say, I am God, I set it like that way, then fine, everything works. But it's a surprise why universe was so close to being flat at early times. Then there are other conditions which I'll just flashing here, but I'm not going to describe them because again this requires some extra explanation. But please ask me if you're interested in these two, the absence of relics as well as why the universe is big and old. That is also a very fundamental problem. Okay, I'll answer if you ask me at the end. Okay. Now there are all this number of problems in the universe. It turns out all of them could be solved in one go. If you propose that, okay, before this thermal plasma state where universe was decelerating and radiation dominated, if ever in the universe there existed a short phase which happened, there was an event which happened in the universe. It happened only for a fraction of a second, and within that fraction of a second, universe was accelerating rather than decelerating. So you need an accelerated expansion of space prior to this hot Big Bang phase. If you assume that, all the problems are solved and much more happens, which we'll talk, but all these problems are solved in one go. Okay. So, but to have accelerated expansion of space, you need repulsive gravity like dark energy. And you have to have it prior to a time when universe was 1 second old, because we know the history of the universe from 1 second till today very, very well. Okay. This short phase of accelerated expansion in the universe is called cosmic inflation. And if cosmic inflation happened in the universe, then it will set all those initial conditions which seem to be unnatural, all of them will become natural. If space is accelerating, then the curvature will always not deviate from 180, some of the angles of the triangle, but it will go towards 180. Okay, so that's why it was so close to 180, because there was a period of cosmic inflation. It will make a universe smooth over large scales, because anything that we see today on large scales was a part of a small place. before cosmic inflation, and inflation stretched them out. Okay? And it explains basically everything. So before I start to explain you cosmic inflation, let me put you in the time frame of the universe correctly. Today, the age of the universe is about 13.8 billion years. Okay, and the temperature of empty space today, empty space means space filled with photons. Actually, it's not completely empty. Is about 2.73 Kelvin. The first stars were formed when universe was about 100 million years old. The first atoms were formed about 4 lakh years. So that is the time when CMB was emitted. About 3 minutes, when universe was only 3 minutes old, the first nuclei started to form, helium nuclei, deuterium. That was a time when universe was really hot, 10 to the power 10 Kelvin, so 1 MeV temperature. And then the electroweak unification, which I was talking about, this gives mass into standard model particles. That happened when universe was about 10 to the power minus 10 seconds old. Cosmic inflation probably happened before that. Okay. So definitely before 1 second, and most probably before 10 to the power minus 10 seconds. But after the beginning of universe. Ask me at the end, what do I mean by beginning of universe? Okay. But after time t equal to 0. And before 1 second, it happened. So it lasted for a fraction of a second. It's a period of transient and rapid accelerated expansion. It is transient because it did not last forever. It lasted for a while. Rapid because at that time the expansion rate of the universe was high. Hubble parameter was high. So if universe accelerates, then it's really super rapid. Okay. And this is the before the beginning of the hot Big Bang plasma phase. Now in Einstein's theory, if you have to have acceleration, Einstein's theory naturally leads to deceleration because there is a negative symbol, but you can have acceleration if rho plus 3p is negative. So you need negative pressure basically. So for acceleration, rho plus 3p has to be negative. So pressure has to be less than minus 1/3 of rho. So you need some substance, which if you leave them, they don't try to push you, they try to pull you. So it's like a stretched rubber band. Okay. If you have a stretched rubber band, they will pull you. So such system, a system which has negative pressure, they have the property that when they expand, they don't lose energy, they gain energy. Okay. For a positive pressure substance, as they expand, they cool down, they lose energy. But a negative pressure substance, they expand more, they gain more energy. They expand more, they gain more energy. Okay. That is what is a thing that is required for accelerated expansion. Dark energy is also that. And also inflation was that. So we need the universe to be filled temporarily, just for a fraction of a second, with some negative pressure substance. And this substance has to be radioactive. All substance in the universe at early times were radioactive, without a doubt, including Higgs particle, muons, anything which has higher mass would always decay. So this will naturally be radioactive. It will last for a while, and then it will radioactively decay to all sorts of particles like dark matter, photons, neutrinos, and all. And then universe will be filled with all these particles. They will thermalize, and then hot Big Bang phase starts. So inflation happened just before that. And to solve all these problems, to make universe the space curvature to be extremely flat, to solve to make this CMB sky smooth, not over just 1 degree but entire 4 pi solid angle, we need space to accelerate at least by e to the power 60 times in the early universe. Okay. So within a fraction of a second, the space increases by e to the power 60 times. E to the power 60 is roughly 10 to the power 26. So we need 60 e foldings of inflation. If that is there, all problems are solved. Okay. So how do we get this cosmic inflation? How do we have such a material? It turns out in the early universe, in all the fundamental theories we have, the early universe was expected to be filled with something called scalar fields. Okay. Now these scalar fields usually have negative pressure. We will call them inflaton field. I'll explain it in the next slide how it works. So universe will be filled with some field. Like today we are filled with photon fields or electromagnetic field. It will be filled with some field at early times. We'll call them inflaton field. It will be transient, so radioactive. And it will last for a while. It will accelerate the universe and then it will stop accelerating. So universe goes into deceleration after that. And within that short time, the scale factor at the end of inflation divided by the scale factor at the beginning should be greater than e to the power 60. That is the condition. Then it should decay, it's radioactive, and then create all the particles we see today. This process in which the inflaton field decays into radiation and matter and stuff is called reheating of the universe. Okay? It heats of the universe. That is the thermal Big Bang phase or hot Big Bang phase. Then begins our good old theory, which is observationally verified and everything works fine. So inflation is a prequel to the hot Big Bang phase. Inflation happened first, then the hot Big Bang phase of radiation domination happened. So how do we do it? How do we achieve it? What does it? As I said, scalar fields do it, and they are natural in the early universe. You take grand unified theories, you take supergravity, you take string theory, all of them are filled with scalar fields. Just like electroweak unification required one scalar field, Higgs, all sorts of unifications at early times require more and more and more scalar fields. So they are the dominant participants in the early universe. Now, a typical scalar field will come across with its potential. Okay? A field will have some potential. And for inflation, what you need is a potential of this particular shape. See this shape? So it has some minimum, and then it has some kind of flat shape. Now, when the universe will be filled with this field, the field has some particular value at early times, and it has higher potential. Okay, the height of the potential energy is high at early times. As time goes on, the field value decreases as well as the potential decreases. And after some time, the field comes to zero, and the potential oscillates around zero. Okay, and then the oscillation happens. Now, in quantum field theory, if you have a scalar field which is oscillating in space, that scalar field is naturally radioactive and it will decay to whatever it is coupled to. And that's how reheating happens. I will not talk much about reheating. And again, if you have a question, please ask me later. Now, the density of this scalar field comes from its kinetic energy, so at what rate it is moving, as well as its potential energy, okay, the height of this potential. That's the total density. And the pressure comes to be kinetic energy minus potential energy. So you can see that to have negative pressure, all we need is to have potential energy higher than kinetic energy. To do that, we need a flat potential so that it doesn't roll fast. So it has low kinetic energy but high potential energy. And that's it. That will make the universe accelerate. So if the kinetic energy is smaller than potential energy, universe will naturally accelerate. This is usually, this ratio of kinetic to the potential is usually written in terms of something called the first slow roll parameter. I'm just introducing if somebody was interested in the technical part. So if we have a first slow roll parameter, which is a ratio of kinetic energy and potential energy, you see that Hubble is related to potential energy. So that's why that sits. So kinetic by potential. If that is less than 1, then you get inflation. And the way the scalar field rolls down is like your basic equation. So there is an acceleration term, and then there is a v dash term, that's the force term. The force term comes because of the gradient of the potential, as well as because of the expansion of the universe, you have a friction term extra. So the scalar field would tend to slow down naturally. And if it tends to slow down naturally, it will inflate the universe. After a while, as it falls, it will speed up. And at a certain point, the kinetic energy will become higher than potential energy. So it will stop accelerating. It will go to a decelerating universe. Then this radioactive substance in the decelerating universe will decay. That's the basic idea. Okay. Not only that, we need universe to accelerate, we need it to accelerate at least for 60 e-folds. Okay. So we don't need the kinetic energy of the scalar field to be initially small, but then later it suddenly increases. Then inflation will stop. So we want it to be small for a long, long time. So the second derivative of the scalar field should also be small. Okay. That is usually quantified in terms of the second slow roll parameter. So we have two conditions. One condition to accelerate the universe, second condition to continue this acceleration about 60 e-folds. And so this is the equation which I wrote in the last page. Now, usually inflation happens in the slow roll regime. In the regime where the first slow roll parameter is not just less than 1, but less than 1. It's really small, which means the kinetic energy is less than the potential energy. That is because of this friction term. Similarly, the second slow roll parameter is usually less than 1. So the way the scalar field rolls down is not very fast. It slowly rolls down. So these are the slow roll conditions. But physically, you understand what's going on. It's just moving slowly. If that happens, then Hubble parameter will mostly come from potential because kinetic is ignored, as well as the velocity of the field will be purely decided by the potential's derivative, and acceleration will be negligible. These are the basic equations for inflation. If these are satisfied, which are satisfied for most potentials that we know of, then universe will not only accelerate, it will accelerate by expanding almost exponentially. So we got a special case of acceleration. You can accelerate by, if your scale factor changes as a goes as t to the power 2, t square is an accelerated expansion, right, with increasing. But this will become exponential, so it's a very rapid acceleration. That's what I was saying, rapid acceleration. So to have e to the power 60 folds in a fraction of a second is no big deal, it just happens naturally. Okay. Such a space which expands exponentially is called a de Sitter space. So during inflation, the expansion is roughly de Sitter like, because Hubble parameter is given by the potential, and if you saw the diagram, the potential was almost constant, so Hubble is almost constant. So such a space will be almost exponentially expanding. It's called quasi-de Sitter space. Okay, just 2 slides I'll show, then I'll stop. Now these slow roll parameters, the first one which has to do with kinetic energy, the second one which has to do with how fast the kinetic energy changes of the scalar field. If you have these 2 parameters, the way they evolve is the following. At early times, very early times, these parameters are much smaller than 1. This line is 1, so they are very, very smaller. This is the first slow roll parameter, the second. As time goes on, they increase slowly, and finally towards the end, they become 1. As they become 1, inflation ends. Okay. That is the typical picture. And after inflation, the scalar field, once it drops down, it oscillates and then reheats the universe. So there is a small phase of reheating. And after reheating, we go into the standard Big Bang phase. I'll stop here because it's already 6 o'clock. What I mainly wanted to say, I could not say, but I'll leave it for some future talk. Okay. Please ask me any questions if you have.
You guys can unmute yourself and
Hello?
ask questions that.
Hello. So when inflation started and up to what time it went on?
We don't know when it started. It would have started sometime in the very early universe, when our universe was smaller than 1 second, and it also lasted for a fraction of a second. So by the time universe was 1 second, inflation is already over. Universe is reheated, and you have this thermal plasma state.
So universe before inflation and after inflation was same.
No, before inflation, we don't know what happened. After inflation, universe became thermal plasma dominated in your standard theory. Not only that, inflation made the curvature of space to be almost 0. So that's how the initial condition which is required is naturally obtained. It made the universe smooth over 360-degree sky. So that's also obtained. And other problems which Big Bang had, it solved. Before inflation, nobody knows. Maybe inflation has been happening forever. Okay. So there is a classical theorem which says, I'll come back to it later. But it's possible that inflation may be happening since ever. But inflation ended at one point. The 60 folds is a minimal requirement. During inflation, universe would have expanded minimum e to the power 60 times. It's possible it expanded by e to the power 5,000 times.
So I have another question, which is slightly out of context. Like, is our universe finite?
Oh, we don't know. Until we measure the curvature, we cannot say. Suppose we measure the curvature of space, and it turns out to be positive, then it is definitely finite. Now today we have measured the curvature, and it comes out to be 0 up to 3 digits. Maybe it is not 0 in the 4th digit. So based on that, we will know whether it's finite or not.
I mean, universe started from somewhere. I mean, it is expanding from a small place.
Not necessarily. No, that's the wrong idea of Big Bang theory.
So
okay, great question. Let me answer this to everyone. A lot of people have this idea that everything in the space-time was at a small point. That is not true. It's just that your observable universe that you see today, that length scale was very small in the hot Big Bang phase at early times. Maybe space was already infinite at that time. We don't know what happened. So pre-Big Bang, we have no idea what happened. Okay, maybe space was already big, or the modern view, more modern view is space was very chaotic. Somewhere it was contracting and forming black holes, somewhere it was expanding for a while and then contracting, and there was a small patch where inflation happened, and that small patch was blown to a huge universe. So we think it's a huge universe infinitely going on, but it's not really. That's the most modern idea. But all of these are speculative. So
Thanks.
it's not like entire space-time was at a point. That's a very wrong idea. Okay, there is no evidence of any singularity of space-time in the early universe.
Hi, I would like to ask a small question.
Yes.
Yeah, so how are we going to like observe or do something so that we can actually prove actually what was going on back then?
Oh, that was the part which I could not talk.
Okay.
So fortunately, I leave it for a future talk. But that was the main part I wanted to talk. How are we sure what happened before 10 to the power minus 10 seconds? Well, whatever happened, the signature is not going to vanish. If that happened in the early universe, whatever was the signature, it will still be in the universe today. It must be mixed up, it must be tangled, it must be a little bit washed out, but not all signature die out. One simple answer to this is that if gravitational waves were emitted from this event, inflation, and they were 100% guaranteed, then they will be there, they will be traveling to you. Gravitons are not absorbed or emitted so easily. So they will just be traveling to you directly from the early times, and you will just see it. The question is a little sort of similar to asking, how do we know 1,000 years ago universe was in a plasma state? That's because light from that state is coming to us in form of CMB. By looking at that light, we know. Now, light will not come to us from a time before CMB because everything was thermalized, light could not travel. But gravitons will come, and then there are other signatures. The way universe clumps today has to do with what happened in the very, very early universe before the thermal plasma state. That was my main aim of this talk, but
Yeah, so do we know what are you going to observe from those gravitational waves?
Not just gravitational waves. I'll say three things. First thing, we have to see how the CMB fluctuations behave. So we have to see uh, how many CMB spots we get of 1 degree angle, how many of 10 degree angle, how many of 1 arc second angle, and we see that distribution. Number of spots versus the size of the spot. Now, if anything happened before the hot Big Bang phase, which created these fluctuations, then that thing should predict how this number of spots as a function of size of the spots should change. And there is a prediction, and the prediction exactly matches with observation without any error. Okay, this is one way to look at CMB fluctuations. Now, in CMB fluctuations, you can look at CMB temperature fluctuations, you can look at CMB polarization fluctuations, or relation between temperature and polarization. That is one way. Second way is, whatever happened in the very early universe and created these fluctuations, that data or that information would be stored in the way galaxies are clustering today. So we have to study the large scale structure of the universe to see how exactly galaxies are clumped. And by studying that carefully, we'll figure out what happened in the early universe. That's the second way of doing it. And then there is a third way, is just to look at gravitational waves. But that's difficult because gravitational waves are difficult to detect.
Okay, so the structure formations have any relations with the, I mean, something like the interference pattern or some
Let me
patterns
explain
of
it a
the.
little more. Very good question. So let me put it in physics language because we are all in physics. So we have a differential equation. That differential equation is decided by laws of quantum mechanics and laws of general relativity. So it's Einstein's equation plus some atomic physics, particle physics put into it. That explains the evolution of the universe. And then from observation, we have some idea about how much dark matter dark is. So how much particular term of that differential equation, how does that look like? So we put that. Then the final outcome not only depends on the nature of the differential equation and the terms go in, also on the initial conditions. Okay. So once we are sure about the nature of the differential equation and the components that sit in the equations, then by carefully understanding what we see today, we can know what was the initial condition. That is the basic idea. So initial conditions are never washed out; they are important. Even if you don't directly see them, you would see them in the way things evolve.
Oh, okay, that was very nice. Thank you.
I see Kishore has his hand raised. So Kishore, you can go ahead with your question.
Swagat, so do you want to? I have a kind of speculative question on monopoles. So can I ask it?
Yes, please.
Yeah. So when you say that inflation solves this monopole problem, does it mean that you don't believe in these string singularities which should be associated with this
No, no,
monopole?
no. Good question. No. So what happens is, let me go to the classic monopole problem first, then I'll come back to this. In the classic monopole problem, what happens is that, so we have our standard model of particle physics. We have electromagnetic interaction, we have weak interaction. They have different coupling constant at low energies. But as you go to high energy, around 100 GeV, they both of them meet. That's how electroweak unification happens. They have the same force. Okay? But the strong interaction and the coupling constants increase, which simply means for electromagnetic and weak interaction, at high energy, the electric force is stronger and, and the magnetic force is stronger and the weak interaction is stronger. But for strong interaction, is the opposite. As you go to higher and higher energy, the coupling constant falls. It is very high today, but it falls. It's called asymptotic freedom. Okay. So as you go to very high energy, in fact, you can extrapolate and see where all three of them would meet. That would be around 10 to the power 16 GeV. So for such a theory to work, all three interactions to be the same, one force. In such a theory, you need to incorporate another scalar field. Like you needed Higgs for electroweak unification, you need another Higgs-like field at that time. And if you have such a field, then universe will make a phase transition from above that temperature to below that temperature. Okay? A unified, grand unified forces to unification broken forces. And that phase transition has a particular nature that it produces some gaps in the in space where the old phase is being trapped. What I mean is the following: when you cool water to make ice, and if you look at ice, which is really cold, not all of ice looks solid. There are some water droplets somewhere trapped, right? Such kind of trapping of old phase in a lower energy phase is called topological defect. And these defects could be in terms of a one-dimensional string, they're called cosmic strings. They could be like a surface, they're called domain walls, or they could be just points, like small spherical things. They are magnetic monopoles, and they are predicted to exist. But we don't see them. The number, it was calculated how many magnetic monopoles you should see, and we don't see as many as it was predicted. We have seen nothing. Uh, so one of the possible explanation is after this grand unified phase transition happened, universe went into a phase of inflation. So if universe started expanding exponentially and it expanded for e to the power 60 times within a fraction, anything that existed will be thrown apart so far that we existing here will see none of them. That's the idea. But that doesn't mean they were not produced.
Yeah. So what I was asking is, so even if these monopoles are at are kind of diluted or whatever, I mean spread out, they're at such a low density. As at least I think there is some suggestion that if you have monopoles, there should be some kind of defect. I mean, there should be some kind of singular. As in, basically, they'll affect the topology of the space which they're embedded in order to have
Yes.
some kind of well-defined magnetic vector potential, right? You
Yes.
sort of have to cut the space between the. So will that kind of defect have any observational consequences, even though
Well,
they are very diluted?
it depends. Suppose you had a lot of those monopoles produced, and then inflation happened. Then it's very difficult to see it because they are so far away you will never see them. But suppose some phase transitions happened after inflation was over in the hot Big Bang plasma phase. So they would be there. Maybe their predicted number is low, but they could be there, and then you can see them. And in fact, we are searching for them, especially for cosmic strings.
Okay. And what kind of observational signatures do you expect, just in a general sense?
For magnetic monopoles, you will see some magnetic field anomaly somewhere in space. It's very dense, so it will attract things towards it.
Okay.
For cosmic strings, you will see gravitational waves, extra background of gravitational waves because of cosmic strings. Also, if a cosmic string is passing by, it will distort the CMB light. So a very dense cosmic string passes by, it distorts. So we call them wakes, WAKES. So we look for wakes in CMB data. So far, we have found nothing.
Okay, thanks.
Okay, I see Swarnim has it hand raised. So Swarnim, you can ask your question.
Yeah. Hi. So you said that in this cosmic inflation model, initially there was only this inflaton field until reheating, and during reheating this field decayed into the particles or matter that we know. So why is that required? Why is it not that the matter or similar particle small particles were there before that? Why were they created at reheating itself? Mm.
Oh, no, no, very good question. Let me explain. Just a minute. I'm sorry for the interruption. Vivek, कुछ चाहिए? मैं आता हूँ 5 मिनट में खत्म करते हैं. I'm really sorry. Yeah. The thing is, it is possible that universe was filled with radiation also, and this inflaton field also, and many things. Okay. And you may say, why do I assume that inflaton field was dominating the universe? You don't need to assume. Let's say radiation was dominating, not inflaton field. Now you know radiation density falls as 1 by a to the power 4th, right? So as universe was expanding, radiation density was falling down. But inflaton being in a flat, in a potential, its density was almost constant. So even if you start with any other things, including magnetic monopoles, all of those things dominating the universe, within a fraction of a second, inflation has a lot of energy, it will dominate because its energy is almost constant and other things are falling. Okay. The same is true for dark energy also today. Dark energy is dominating because it was constant energy. No matter how low it is, it will eventually dominate. So it will finally eventually dominate the universe. So any substance which has negative pressure will always tend to dominate the energy density of the universe. This is a fact of general relativity. Okay. Now let me put a second question related to what you asked. Why was the inflaton field decaying only when it started oscillating? Why didn't it decay when it was rolling down? Well, that doesn't work. The scalar field acts radioactively only when it oscillates. If it doesn't oscillate, at least it has to pass through phi equal to 0. If it doesn't pass through that, it doesn't work. It doesn't decay. It doesn't behave like a particle. When a scalar field is rolling down, it behaves like a coherent wave. Okay, something like a superfluid. Okay. So it doesn't decay like individual particles decay. So that's why it's stable. So all of this comes naturally.
Okay, so before reheating, we are just saying that inflaton was dominant, and we are not making a hard statement that the rest of the matter or radiation was not there.
They were all there, but so suppose first, let's say first 10 E folds happen. In 10 E folds, inflaton energy is still the constant, but radiation has fallen by e to the power 40 times, and matter has fallen by e to the power 30 times. So they are almost negligible in the universe. So you have to produce them again because after inflation, otherwise universe will be empty.
Okay, yeah. Thanks.
No more questions?
Yeah, I guess so.
Can I just show one slide so
Yeah,
that it will
sure.
be continuation, and whenever, if at all, we talk again, we come back to it. So I gave you all this beautiful story that it solves all these problems, but it also creates one problem. And the problem is that we achieved this acceleration and we made universe smooth and flat and everything, and it set the right initial conditions, but it made the universe extremely smooth and empty. So we need universe to be filled with matter, so that reheating can do it after inflation. But then everything that will be produced will be completely smooth. If they are smooth, today we will be filled with some dilute gas. So we need something to create fluctuations, right? What about the origin of structure that I talked about? What happened to the initial density fluctuations? Who will create them? Because inflation made everything smooth. Well, since inflation has been solving all the problems in one go, can it also solve the problem of creating fluctuations, density fluctuations? The answer is yes, it can, and necessarily it does. So if you had inflation, it not only made it smooth, it also creates small quantum fluctuations, which was the original aim of my talk, which I could not talk. And just quantum fluctuation will help. Okay, I leave it. Leave it here. Will not stretch. It's already late.
Yeah, so thank you very much. That was a very nice talk. And also, I'd just like to make a small announcement. So I guess in next week we're going to have a last Friday session, right?
Yes.
So
Yes.
yeah, so probably we won't have any session on that day. So our next discussion session will be next Friday. Yeah. So So should I end this meeting
Yeah,
now?
yeah. I also like thank Swagat. So you very accurately conveyed the theme of this talk, that how it is different from other talks that happen in IUCAA. So very much thanks.
Thank you for the questions. At least the talk excited some questions. And I have to answer a lot of questions, so please catch me sometime. Okay. I remember some follow-up questions that I did not answer. It just got
Yeah,
delayed.
yeah.
So, yeah.
Yeah,
Thanks.
sure. Okay.